All right. So today we'll talk about hydrogen. Why? What do you know about hydrogen? What do you think this is?
As in, like the element, or as in
So this is a mechanism and this is a way to store energy.
or storage?
Yep. All right. So why aren't we adopting solar and wind?
Why we it's
Huh?
clean
No. Why?
or so? Oh,
It's the cheapest source of energy. Why aren't we still adopting wind and?
it's not as efficient.
What do you mean it's not as efficient? Electricity is the most efficient thing.
Like it, the amount of money you put into it, it's not always working.
It's the cheapest source.
Is it because the technology isn't there yet?
Hmm?
Is it because no, the batteries?
The batteries, okay, the sun doesn't shine at night and the wind is not blowing at all times. So you need batteries to store energy. If the batteries were cheap, then everything would be running on wind and solar. Because when they're not blowing, you just have stored the energy in batteries. So batteries are expensive. This is another way to store energy. Okay. So let me show you what the future would look like.
Is
Okay.
it hydrogen flammable?
Yeah.
Is it hydrogen?
Hmm?
Is it hydrogen?
Yep.
Yeah.
Mhm.
That. I can't believe they did that though.
What's that?
I can't believe they did that though.
Yeah, yeah.
They were like.
But, well, I mean,
They were like
the Artemis uses liquid hydrogen as fuel. Okay. So here is a carbon neutral future. Okay. So you would get electricity from wind and solar. Okay. And what you do is with this electricity, split water. H2O, 2H2O plus electricity. So what is electricity? What is electricity? Energy. So you take water, add energy, okay, and then what you get is 2H2O, 2H2 plus O2. So if you pass electricity through water, you can split it into hydrogen and oxygen. So where did this energy go? This energy got stored there. Okay.
Is that why water is such a good electric conductor?
Well, you have to mix an electrolyte in it. In water, it's
Salt water.
yeah, salt water. Salt water is a better electrical conductor than just pure water. In pure water, only a few molecules are split. Okay. So we're talking about hydrogen. It's a mechanism to store energy. Okay, so here's the basic. Uh, so let's make sure we understand this. So you take water, pass electricity through it. What is electricity? It's energy. So you're adding energy, and this will split it into hydrogen and oxygen. So that energy got stored here. Okay. Now, what's the good thing about hydrogen? How long can you store it?
For a while.
Huh?
For a long time.
Forever. For a long time. Okay? You can store it forever. Okay, so how do you extract this energy? You can put it in a fuel cell. This is a fuel cell. And you can pass that hydrogen. Hydrogen is fuel for the fuel cell, and get electricity out. Okay? So right now, so this process, passing electricity through water and producing hydrogen, the maximum efficiency is about 80%. So 80% of the electricity and energy stored, 80% of the electricity you spent got stored in there. Okay? And when you use hydrogen as a fuel in a fuel cell, the most efficient this is 80%. So now, so the net efficiency 80% is 0.8, and then the second process is 0.8. So 0.64 is the efficiency. So 64% is your net efficiency. Okay, what that means is, let's make sure we understand this. When you put $100 in the bank, how much do you get back?
64.
Yeah, so when we put money in the, very good, so you got it, okay? So you put $100 in the bank, and you got back 64. But this $100 was for free, and we're willing to do it, okay? So this is the future. And what's great about it? You're producing electricity without any carbon dioxide in the atmosphere, and you're able to store that electricity and get it right back whenever you want it. Okay? So right now, this process is expensive. Fuel cells have been around for 150 years. Okay, well, and they were expensive too. The catalyst there is expensive, but they are getting cheaper. Have you guys heard of hydrogen cars? Has anybody seen a hydrogen car? Okay. Well, you can go to Kennedy Space Center and they have a hydrogen fueling station. And so this would be a fuel cell car. Okay. So here's the hydrogen tank. Okay. And here's the so so here's fuel cell. So the fuel cell produces electricity to the electric engine, and so here's hydrogen coming from there. And here's the fuel cell, and you can store the electricity in a battery, and the battery can also drive that, or the electricity produced directly can go to the engine. Okay, so or you can burn hydrogen. Okay, now what do you think might be the problem? Hydrogen is a very light gas, and storage is the problem. It takes a large volume. You know. So what you could do is store hydrogen in between metals. So this is metal hydrides. Okay, what do you think is the problem with that? So huh? This metal is heavy. So you have a heavy tank in your car. Okay. So how would you like to be driving around with 1,000 pounds in your trunk? Okay.
It would take more fuel for it to even work then too.
But if the fuel is free and no carbon dioxide, okay.
So like the tank would have to be bigger because all the weight can be more like energy to push it.
Well, so longer the range, the heavier the tank. Okay. So, these fuel cells are used in forklifts and stuff like that. They've been using it in warehouses and forklifts and stuff like that. Have you seen any of these? No. Okay. All right. So now, do you get a good picture of it? Okay. So now we'll go through the slides again. Let me summarize this. Here's the green future. Okay. The problem with, again, solar and wind are the cheapest sources to produce electricity, but they are not available 24/7. So we need a mechanism to store the electricity produced by these technologies that can be used when at night or when the wind is not blowing. Okay, so you store the electricity in hydrogen. Okay, so you can use electricity to split water. You can use electricity to split water into hydrogen and oxygen. This is where the energy is stored, and that hydrogen can be used in a fuel cell to produce back electricity. And this whole process has zero carbon footprint, operational. Okay? And that's always the goal. All right, so let's go through the slides. Look at this. Um, energy per kg. So the energy per mass per pound. Gasoline has 50 megajoules per kg. 1 kg is 1,000 grams, which is about 2.2 pounds. Okay. Look at the energy content of hydrogen per kg. It has 3 times the energy of gasoline. But what is the problem? It occupies a large volume. Okay, so all right, but hydrogen has a high energy content. Okay,
Like 3 times it.
what's that?
Like 3 times it, isn't it?
Yeah, 3 times. Yep. Yep. So energy supplied to produce hydrogen can be recovered by burning the hydrogen or using it in a fuel cell. So you can burn it just like gasoline, okay? And Artemis, uh, the rocket we sent to the moon recently, uses liquid hydrogen as fuel. Okay? Um, I believe Starship also uses liquid hydrogen. I believe so. Okay, so. So we'll learn how to produce hydrogen by various ways. I already showed you how to produce it via electricity. Okay. The combustion of hydrogen produces water. So when you burn hydrogen, again, you're just producing water and energy, okay, and heat. Okay, so again, there's no carbon footprint to it. Okay. So here is what this is showing is specific volumetric energy densities. So just to show you that hydrogen occupies a lot of volume. Okay. This is a meter cube. Okay, this thing. This is so a meter cube. Okay. Hydrogen. So energy per kg. This is you saw per kg per pound. It's got 3 times the energy of gasoline. So what we're trying to do is see if you can use hydrogen in your cars. Okay. So it's 3 times the energy per gasoline, but energy per meter cube, and this is at 1 atmosphere pressure. So this energy, if you had this much hydrogen, you only get 12 megajoules of energy. If you had that much gasoline, you get 35,000 megajoules. So, you know, volumetrically, gasoline has much more energy. You know. So if you can figure out a way to compress hydrogen and store it, okay. So that's what we tried to do. We tried to put it in spaces between metals. You know. Now the problem with that is if you can, it's hard to, you know, you can pump it in and then it's hard to get out of the metal as well. So okay. So a zero carbon footprint scenario is illustrated in the diagram. Produce electricity, split water, use the electricity to split water, and then you've stored this energy here. Okay. Split water, you can store hydrogen as long as you want. And then when you need the electricity back, use the hydrogen in a fuel cell. Okay. So in principle, this is 64% efficient. The energy can be recovered 80% for electrolysis and 80% for fuel cell. Okay. So hydrogen is a mechanism for storing energy. How do you produce it? You can produce it via electrolysis, that is split water using electricity. Thermal decomposition of water. What does that mean? Just heat water.
Evaporating?
Huh?
Evaporating?
No, just heat water to high temperatures and it'll split. And chemical reactions. So we'll look at all these mechanisms. So again, here's the basic basic equation. You take water, supply energy via electricity. This is electrolysis, and that splits water into oxygen and hydrogen, and that energy got stored here. Okay. Energy supplied by electric current is stored in the form of chemical energy. So in this process, what you have done is you've converted electrical energy to chemical energy. Okay. And this will give you numbers. Okay. So electrolysis, there are two main types of electrolytic technologies, alkaline and proton exchange membranes. Okay. So here's the important number. Industrial production of hydrogen has a specific energy of 143 megajoules per kg, which has a specific energy of that much, requires 200 megajoules of electricity. So you can use, in industrial situations, you need 200 megajoules of electricity to produce 1 kg of hydrogen, which stores 140 megajoules. So 30% of 200 is 60. 200 minus 60 is 140. Okay, so and on an industrial scale, conversion from electricity to chemical energy stored in hydrogen is 70% efficient. Okay. So right now. Yeah. Again, this might sound bad, but when you burn gasoline, how much of that gets converted to motion in your car?
Was it a quarter of it?
Yeah, just a quarter. So we've been living with that all along. Okay. I'll tell you, give you another example. Would you come to this class if it was hot and humid? No.
I paid for it, yeah.
Huh?
And I paid for it, yeah.
You want to be comfortable, right? I mean, we want to make it comfortable around you. Look at this. We're cooling the whole building. How much?
I'm usually cold, so I
Yeah.
don't have a thick jacket.
Yeah. No. But the point is, if you could figure out a way just to make the air around you comfortable, rather, yeah, right? So we do use these inefficiencies all over.
It's worse when it's hot, though, yeah.
Hmm?
So it's worse when it's hot, and you're cold, so put on a jacket, yeah.
Yep. All right.
But humid in here, like a boiler, summers.
You know what the humidity is in this room? To make it comfortable, it's about 50%.
Hmm.
That's the main job of the air conditioning, to remove the moisture, more than the temperature. All right, so here's the basic process, electrolysis process. Again, what is electrolysis? You're using electricity to split water. Okay. So here's a battery. Okay. So a battery is just a store of electrical energy. You're going to use some of this electrical energy and split the water. Okay. So here's an electron travels from here. Okay. And so this water gets split into hydrogen and 2 hydroxyl ions. So you had to get 2 electrons. See, there was no this is neutral, and now you have 2 negative ions. So you absorb 2 electrons, and that's where these electrons came from. Okay, from the battery. The electrons came from the battery. And now these 2 guys they become negative ions, and they're repelled by this cathode, and they travel here. And then they'll give up their electrons here, which the electron goes out and comes back to the battery. Okay. So what happens here? At this point, the two hydroxyl ions get there, and it's this guy splits into, okay, so we'll take 4 hydroxyl ions, and this becomes O2 plus 2H2O. Okay, there are 4 oxygen atoms, 4 hydrogen atoms, and so here's 2 oxygen atoms, and here's 2 oxygen atoms, and then 4 hydrogen atoms. So this reaction happens, and 4 electrons go from here and comes back here. Okay. The net effect is, so this is the net effect. So 2 water molecules plus energy from the battery got converted to, so this energy was used to split this water molecule, became oxygen and 2 hydrogen atoms. Okay, so this energy got stored there. So that was the process. Okay. So hydrogen bubbles up at the negative, at the cathode, and oxygen bubbles up here. Okay, and you can use oxygen for various other things. So this is a byproduct, a useful byproduct. Okay, and this is where your money is. Okay, so that's the electrolysis process. Okay. Do you guys understand that? Okay. The electrical conductivity of water is increased, so that, remember that negative ion had to travel from here to there. This electrical conductivity can be, of water is increased by dissolving an ionic compound such as sulfuric acid or potassium hydroxide or the like. Okay. So hydrogen can be used to store renewable generated electricity when it's not needed, and then used to meet power needs when needed to fuel vehicles. The storable quality of hydrogen helps makes hydrogen an enabler of wider use of renewables. Yes, so right now a lot of, you will hear in the news, a lot of countries are looking to produce green hydrogen. This is what that means. Okay. Green hydrogen means producing hydrogen using electricity generated by solar and wind. Okay. So now we will look at hydrogen production from other ways. Thermal decomposition of water. You're decomposing water using heat. Okay. So you can, so heat can be either generated from solar energy, or you can, people also use heat produced in nuclear power plants, in coal power plants and all that. But you want to be green, so if you want to be green, then you want to use solar heat or heat from nuclear power plants. Okay. So decomposition of water can be accomplished using thermal rather than electrical energy. A catalyst facilitates this process. What does a catalyst do?
Sets into motion.
What's that?
Sets into motion. Starts a reaction.
A catalyst, the job of a catalyst is to make a reaction go thousands of times faster. Okay, so if you didn't have enzymes in your system, in your body, that burger would take 2 years to digest. Yeah. So
Speed up the process.
what's that?
So speed up the process.
It speeds up the process. You know, a catalyst, that's what it does. Okay. So you have a catalytic converter in your cars, because if you didn't have the catalytic converter in your car, out of your tailpipe you'd be getting a lot of carbon monoxide. Yep. And you turn on your car in your garage, you'll pass out pretty soon. So that catalytic converter converts that carbon monoxide into carbon dioxide. Okay, so it helps in making that process go faster. Okay. So now we're going to use heat to split water. Okay, so here's heat. Uh, so I'll typical thermal decomposition reactions begin by heating sulfuric acid, and so what you have is a mixture of sulfuric acid, water, and iodine. So you take heat sulfuric acid, and this splits into oxygen, sulfur dioxide, and water. Then this the sulfur dioxide is heated further in the presence of iodine and water. Uh, so hydrogen iodide is formed, and you got back sulfuric acid that you started with. Okay, so and then this iodide gets the heat splits that into hydrogen and iodine. Okay, so you used heat, and uh, eventually that water got split into hydrogen. There's the hydrogen and there's the oxygen. Okay. So there were several intermediate steps, but essentially what you did was you took heat, and in the presence of all these guys, you got oxygen and hydrogen. Okay. So if you multiply everything by 2, you'll get 1 oxygen molecule and 2 hydrogen molecules. Okay. So all this heat got stored into the hydrogen. Okay. So this is thermal decomposition of water, and here's high temperature electrolysis. Okay, what this process is, so when the energy supplied is in the form of heat originating from solar, thermal, or nuclear, the best path to production of hydrogen is through high temperature electrolysis. So if you're getting heat from the sun or nuclear energy, the best way to produce hydrogen is through high temperature electrolysis. What that means is, see, if you take water and heat it to, let's say, 1,000 degrees Celsius, so it's steam now, and now you pass electricity through steam, so you've given this much energy on steam. Where did that heat come from? Solar or nuclear energy. And then you pass electricity through it. Okay, so this would be the total energy spent, okay, at this temperature. And this is less than energy you would spend on water, electrolysis of water. So see, if you electrolyzed water, that's how much energy you would spend. And if you electrolyze steam, that's the total energy you spend, which is less. Okay. So research into high temperature. So what is electrolysis? A high temperature electrolysis? You use some source of heat to boil water to produce steam, and then you're passing electricity through steam to split it. Okay? So that's what that is. Research into high temperature electrolysis and high temperature nuclear reactors may eventually lead to hydrogen supply that is cost competitive with natural gas steam reforming. Right now we produce a lot of hydrogen is produced that way. Okay. So you have a nuclear reactor, and there's a lot of waste heat. If you could use that heat to produce the steam through which you can pass electricity. Okay. So that would be a cogeneration facility. That's what those things are called. Okay. So natural gas reforming. What is natural gas? It's mostly methane. It's a combination of methane and ethane. Okay. So what we're going to do is we're going to extract hydrogen from methane. Okay. And so what high temperature steam is used to extract hydrogen. In steam methane reforming, methane reacts with steam under about 20, so 3 to 25 bar pressure. Bar is almost 1 atmosphere, so about 20 atmosphere pressure in the presence of a catalyst to produce hydrogen and carbon monoxide. Okay, so this is methane, natural gas, and this is high temperature steam. They'll combine in the presence of a catalyst, making the reaction go faster, and carbon monoxide and hydrogen is produced. And this carbon monoxide and steam react, this carbon monoxide reacts with steam to produce carbon dioxide. So you don't want to release carbon monoxide in the atmosphere. Yeah. So you can use methane and steam, high temperature steam, to produce hydrogen. Okay. The overall process is 65% efficient. Okay. So if you used 100 joules of heat, 65 joules of heat of that energy is stored in the hydrogen. Okay. So here, natural gas wells, you get steam, and and you get water, and this is the again, steam methane reforming um, reactor. You get hydrogen out, and the carbon dioxide can be sequestered back into the gas well. Okay, you don't want to release carbon dioxide in the atmosphere. Okay. All right, so you've learned uh, 3 methods of producing hydrogen: electrolysis, thermal decomposition of water, okay, and high temperature electrolysis, and natural gas reforming. Okay. Of course, this is what you want. Okay, electrolysis is what you want because you can use electricity from green sources. Okay, and right now it's a little expensive, but it's getting cheaper. Okay, and so that's what you'll be using in the future. All right, so here's so let's say you want to be able to drive your car on hydrogen. When you burn hydrogen, what is the output? Energy and water. And that's what would be coming out of your tailpipe. If you use hydrogen in a fuel cell, that's what will be coming out of your tailpipe, just water.
Like steam.
Well, it won't be steam, but yeah. Okay. All right, so this is showing you various mechanisms to, so this would be a hydrogen gas tank, okay? If this was just hydrogen at 200 atmospheric pressure, this is how much the tank would be, the volume of the tank, okay? To give you a reasonable range, okay? If you could store it as liquid, this is the volume it would occupy. But liquid is very cold, so that's not practical. Okay. This is so here's a way to store it in the metal, and here's another mechanism to store it in a metal. Okay, so hydrogen has a very low density, and its volume must be reduced in order to store and transport it efficiently. Okay, so if you want to use there. But if you want to just produce electricity in a fuel cell, you can store hydrogen in big tanks and then convert that back to electricity. Okay. So you can have compressed hydrogen gas, liquid hydrogen. Again, you have to be very cold, and metal hydrides. Okay. So you store the hydrogen in between the spaces in metal. So you produced hydrogen, and now you want to store the hydrogen. Okay. So a factor to consider for storing hydrogen is efficiency of the process. How much energy is needed to store the hydrogen? Okay. Let's say you just store energy without hydrogen without compressing, then you don't need any energy. But what is the problem there if you don't compress hydrogen? it takes up large volume, so you'd have to have very large tanks. Okay. In the case of compressed hydrogen gas, the energy needed is, so you need energy to run the compressor. Okay. And this energy is lost and not recovered when the hydrogen is utilized. And typically about 10% of the energy content of the hydrogen is used up. So if you're storing it in compressed uh, gas form, so you spend 10% of your energy compressing the hydrogen. Okay. So this is compressed hydrogen gas at 35 megapascals. Okay, so 10 to the power of 5 pascals is 1 atmosphere. So this is 350 atmospheres. Okay. Uh, uh, and so this is what this is storage capabilities of 0.1. So this is 100 liters volume of hydrogen in different forms. Okay, so you're storing 100-liter volume of hydrogen gas. 100 liters is roughly, okay, so if you take this much hydrogen, 1/10 of this, okay, so this much hydrogen. And you're storing it, so if you store it at 350 atmospheres, this is energy per volume, so that's megajoule per 100 liters. So this is, you're getting 300 megajoules per 100 liters, and in gasoline you would get 3,500. Okay, so the energy, volumetric energy density of gasoline is much higher. Okay, and that's why we're still using gasoline, and it's easier to pump and all that kind of stuff. Okay. This just shows you density and pressure relationship. So a bar is 1 atmosphere. This is 1,000 atmosphere. So there is the volumetric energy density, okay, kg per meter cube. See, liquid hydrogen is the most dense. Okay. You can compress the hydrogen gas to 1,500 atmospheres and still you're storing more hydrogen in liquid hydrogen. Except that this is very cold. You have to spend money cooling, liquefying it. Okay. So this just shows you the density of hydrogen. Okay. What you want is to be able to store more and more hydrogen. Okay. And the denser it is, the less volume it will occupy. Okay. Liquid hydrogen. Hydrogen may be liquefied by lowering the temperature to 20 Kelvin. Okay. So that's quite cold. Liquid nitrogen is 77 degree Kelvin. Okay. The density of liquid hydrogen is greater than compressed hydrogen gas at any pressure. So you can increase all the pressure you want, but you can never reach the density of liquid hydrogen. Okay, there's another thing you need to consider when storing liquid hydrogen. Okay, all this stuff can be relevant because FPL can do all of this. Okay, so for instance, a utility company, they can produce electricity using solar and wind, produce hydrogen, store hydrogen efficiently, and turn it back into electricity. Okay, when that becomes cheap enough. Okay, so what is hydrogen? It's H2. So you have 2 protons, and here's an electron. And this electron pair is shared, okay, between the 2 guys. Okay. These protons have spins. The protons are spinning. So you use your right hand, and if it's spinning like that, if your fingers point in the direction of spin, so that is your thumb points in the direction of the spin. Okay, so there's the spin. If the spins are anti-parallel, this is a low energy configuration. If the spins are parallel, this is a high energy configuration. So in this hydrogen gas, depending on how the spins of the protons are, here's a high energy configuration and this is a low energy configuration. What happens is when you cool hydrogen and make it into a liquid, okay, 75% of the hydrogen in the liquid is this ortho hydrogen. And then when you've cooled it into a liquid, this turns into that and it releases heat and some of your hydrogen becomes gas. So that's the problem. The anti-parallel alignment is parahydrogen. Parahydrogen is the ground state. And the parallel alignment, this is orthohydrogen, is the excited state. At room temperature, thermal energy causes the mixture to be 25% parahydrogen and 75% orthohydrogen. This is 25% this and 75% that at room temperature. And now you cool this and make it into a liquid and you get 75% of that. Cooling hydrogen quickly to the liquid state yields a non-equilibrium excess population of orthohydrogen. Okay, so when you cool it, you get an excess of this stuff. And the orthohydrogen gradually converts to parahydrogen, giving up energy and causing some of the hydrogen to boil away. Okay, so thus some of the energy used for cooling is wasted. Okay. Typically, the energy required for liquefaction compared to the energy content of the hydrogen is 30%. So to convert hydrogen into liquid, it costs you 30% of the energy content of hydrogen. So you're wasting that much energy. And why are you wasting that? So you can store a lot of hydrogen in a small space. Okay? So if it's worth it to you, you do it. Okay. Here's a way to store hydrogen in metals. Okay, hydrogen can be stored in a metal by the formation of a metal hydride. So this is what you would do if you wanted to use hydrogen in a car. So the hydrogen tanks, in a car, they are some metal which will allow hydrogen to be stored in the spaces. Okay, so you pump hydrogen, splits it, it's stored in atomic hydrogen, and then when it comes out, it becomes hydrogen back. And then you either use this in a fuel cell or burn it in an internal combustion engine. Okay? You could actually burn hydrogen in your internal combustion engine. Okay? Hydrogen can be stored in a metal by formation of a metal hydride. Okay? So titanium, a common metal for this process is titanium. So two drawbacks to the approach are difficult to get hydrogen in and out of the metal quickly and excessive weight of the metal. All right, now let's talk about fuel cells. So you produced hydrogen. We've talked about production. And then storage. And now what we want to do is produce electricity back. Get the energy out. Okay. So fuel cells transform the chemical energy in the hydrogen to electricity. All right, so here's in a fuel cell, hydrogen goes in. You take the electrons out of the hydrogen. These electrons go through the load, and so this electricity is doing the work. Okay, so the energy stored in the hydrogen is extracted, converted into electrical energy. This energy does work outside, and these electrons are, so the hydrogen is stripped off its electrons, and it becomes protons, positive ions. These positive ions travel this way. These electrons went out in the external circuit, did work, and then came back, and these electrons are given to the oxygen that comes in. You got positive hydrogen ions going that way, the negative oxygen ions coming this way, and these two combine and become water, and that's what you get out. So the energy stored in the hydrogen is converted to electrical energy, and that's what the fuel cell does. Okay? Fuel cells produce relatively few pollutants, okay, so essentially no pollutants, compared to conventional combustion-based power generation technologies. They are fuel flexible, okay? You can use other fuels besides hydrogen. Okay. Fuel cells were invented in 1838. The first commercial use of fuel cell came more than a century later in NASA's space program to provide power for satellites and space capsules. Okay. So nowadays, they're used to power fuel cell vehicles, including forklifts, automobiles, buses, boats, motorcycles, and submarines. Okay. So the most uses in forklifts. There are many types of fuel cells, but they all consist of an anode, cathode, and electrolyte. So here are the electrolytes, different electrolytes. Okay. And here is a solid polymer. This is a proton exchange membrane, and the efficiency of that is 80%. That's the most efficient. The other guys, look at that, the efficiency is 60 to 70%. What does this 80% efficiency mean? What does the 80% efficiency of the fuel cell means?
It gives back 80% of what you put in.
So there's chemical energy stored in the hydrogen. If 100 units of chemical energy was stored, 80% of that is converted to electricity. Okay, so that's what that means. Okay, so what happens here is, again, you put in hydrogen, okay? So electrons, so the anode contains a catalyst that causes oxidation of hydrogen and generating hydrogen ions and electrons. Okay. At this place, there's a catalyst that strips the hydrogen of its electrons, and it makes it into a positive ion, and these electrons travel to the external circuit. So there's a catalyst here which strips the hydrogen of the electrons, and then these hydrogen ions travel this way. The electron is given to the oxygen, which makes it a negative ion, and these two combine and form water. Okay. So the chemical energy stored here is converted to electrical energy. Okay. So the anode contains a catalyst that causes oxidation. The hydrogen ions are then drawn through the electrolyte towards the cathode after the reaction. The electrons travel through an external circuit. They travel through an external circuit doing work. At the cathode, hydrogen ions, electrons, and oxygen react to form water. Fuel cells are classified by the type of electrolyte that is used. All right, so again, hydrogen at this place, at the anode, hydrogen in the presence of a catalyst is stripped of its electrons. These electrons travel out through the external circuit, or it could be the electric motor driving your car. And these electrons combine with oxygen, and the oxygen gets the negative charge. And then the proton and the oxygen combine to form water. Okay. So that's the fuel cell. Okay. So fuel cell, many automobile manufacturers are developing fuel cell vehicles. Toyota is betting big on this thing. Okay. So, and Elon Musk's Tesla is lithium-ion batteries. Okay. So these vehicles use electricity produced from hydrogen to run electric motors, and sometimes use batteries and supercapacitors as an additional energy source. Okay. Now, See, gasoline, when we first adopted gasoline, we didn't have gas tanks everywhere. Now there are gas tanks everywhere. So let's say you want to use hydrogen cars. You need hydrogen fueling stations everywhere. Okay? And the density of hydrogen fueling station is very little. See, none of these states have hydrogen gas tanks. And if you want to switch to that, it takes a while. Okay. In Florida, actually, we only have a hydrogen station at Kennedy Space Center. We've had that for quite a while. Okay, so hydrogen is an energy storing mechanism. Okay, and it'll play a crucial role in your zero carbon footprint future. It's commonly produced by electrolysis. Okay, and this process is getting cheaper by the day. It has a very high energy content per unit mass. Per pound, it has energy content 3 times that of gasoline, except that it occupies a large volume. Its low density by volume makes storage and transportation a challenge. Okay. But if you're FPL, you don't care. You just build large tanks and. Compressed hydrogen gas is the most common approach to storage. So, and hydrogen fuel cells are under development. Okay. All right, guys, so that's hydrogen. That's the alternate battery. Okay. And that and